All right, I would like to welcome everyone to our seminar of mathematical physics. And today our speaker is Caleb Jonker, who is going to tell us about generalized Kähler Ricci flow as a Courant derivation. Somewhat.
Thank you for the introduction. Yes, so this is a project which came out of my PhD thesis. And the goal is to tell you something about the structural aspects of generalized Kähler Ricci flow. I think there's still a lot that's not understood, but hopefully I give a slightly clearer picture. So I'll start with some motivation. So generalized Kähler geometry came out of physics in the 1980s, and physicists were studying sigma models. We have maps from some surface to a manifold with the Riemannian metric, and there's some action functional on these maps. Describes the physical system, and what they found was that there is n equals 2, 2 supersymmetry precisely when M is generalized Kähler. Means that M and G, and in addition, you have a pair of complex structures which are compatible with G. And you emission structures. And there's an integrability condition which says that DC plus omega plus equals DC minus omega minus. You can call this one H. And
What is DC plus minus?
Yeah, let me say. So I have a pair of complex structures, and for each complex structure, I can produce a DC operator, which is I del bar minus del, the real operator on the space of differential forms. And then we have the remission forms G. Okay. And
so G is metric and is remission with respect to both complex.
That's right. Yeah. Yeah, that's what it means.
Okay. Yeah. And they're both integrable.
They're both integral complex structures. That's right. So this is what generalized Kähler geometry is, and it's also important for the physical system is knowing when you can quantize it. And in order to do that, you have to do this process called renormalization group flow. And the physicists found a particular form of renormalization group flow for a Riemannian metric. Then much later, it was discovered that you could actually extend that flow to a flow of the whole generalized Kähler manifold. So that's the flow that'll give you. It's called generalized Kähler Ricci flow. It was discovered by Streets and Tian. In 2010. This dot you have this set of equations where, so let me tell you what everything is. Ricci is just the usual Ricci tensor for the Levi-Civita connection. H squared, that's only what H is over here. H squared is a symmetric true tensor. You contract H with a vector field, and you make the pairing using G. Theta is what's known as the Lie form. Is d star of omega composed with complex structure. This gives you one form.
So probably the other second y is also an h, right? So it's,
Oh yeah. Thank you. Okay. And of course, there's two of them coming from a pair of complex structures.
By sharp, you mean to link them to
Mainly
race index?
That's right. Yeah. So I have a one form. I use the metric to produce a vector field. Okay. So what you'll immediately notice about this equation is that it has this annoying asymmetry where I plus is fixed and I minus is not. But this can easily be resolved. This can easily be resolved because we're just dragging I minus around by some vector field. So you can make it symmetric if you prefer, but I won't. Okay, so that was what the generalized Kähler Ricci flow was, and now I'd like to spoil the rest of the talk by giving a reformulation, which I'll try and explain for the next hour. So there is Courant derivation. Actually, let me first. Generalized Kähler structure can be repackaged. As a triple consisting of a pair of real Poisson structures and a holomorphic Poisson structure with respect to pi plus. So these are real Poisson. Is holomorphic. And again, the asymmetry is appearing, but I could also put one here, it doesn't matter. You can use either one. Second part is that generalized Kähler Ricci flow can be described Courant derivation I'll call R minus plus acting this triple. And you don't know what any of these words mean yet, but so far, what you can think is that this Courant derivation, what it really is, it's a vector field on some space. And what we're really doing is we're dragging around these tensors by some vector field. So, okay. Now let me, there's no questions about this so far meaningless statement. Let me eliminate that to an experiment. So,
So these Boston structures in particular encode the metric.
yes, they encode the metric and the two complex structures are present there. Yes. That's what I mean.
So you differentiate with respect to one parameter group, with respect to one parameter. In the case of flow, G prime and G dot is.
It's like all the
Yes,
So
yeah, that's
one parameter,
yeah, that's right. It's like the Ricci flow.
It's not in the sigma. Sigma is two-dimensional and just on.
Sigma, yeah, you should, from now on, you should ignore sigma. Sigma was the motivation.
Yeah.
That's how the physicists came up with these things, but
Yeah,
generalized Kähler geometry is just on the target. It's nothing to do with the principles.
parameter is the sort of energy scale or logarithm of the energy scale.
Sure. Yeah. I don't know. I believe you. Okay. So the first step, well, is a very, yeah. So the first step is due to Gualtieri. Gives not the repackaging that I've given, but another one. Does that generalized Kähler geometry is equivalent to a pair JA, JB of complex structures on the bundle T, which is T plus T star, and G plus cotangent. By which I mean that, yeah. So they're just operators which square to 0 on this bundle, or square to -1 on this bundle. And they should satisfy compatibility with first of all, there's a natural pseudo-metric, this pseudo-Euclidean metric on this bundle, which is given by a vector in one form. We just pair the one form component with the vector, and vice versa. And by compatibility, I mean, well, it's a complex structure, so you could mean two things, but they're the same. Just mean this. And secondly, I want compatibility with a natural bracket on this space. You take the lead brackets with the vector field components. Take this non-skew symmetric operation, and then you can twist it by adding term involving a 3-form H. In this case, the 3-form is the same as the one there. And compatibility means since J squares to 0, square to -1 has a plus I eigenvalue. L A B. I want this thing to be involutive with respect to this. So this saying that saying that a maximal isotropic of T plus Tm is involutive tells you that got a name, it's called a derivation. In particular, the bracket on T plus Tm restricts to a Lie bracket on here. So you get a valid approach. So let me write out how this equivalence goes.
You also want some positive definiteness for this one?
Right, of course, yeah. Thank you. Yeah. So the positive definiteness condition looks like. That's this is positive definite. So how do you do this? Well, this is an operator acting to answers in this way. Very similar, but stop setting minus signs in certain places. And so I can already tell you what pi A and pi B are. In particular, if I look in the top corner here, that this is a map from T star to T. And in particular, it's a bivector. Integrability of J tells you that this thing has to be Poisson. So this is pi A.
This is generalized Kähler Ricci flow in this sequence with this triple inversion.
Can I see generalized Kähler Ricci?
Yeah, so I mean, we will get one triple inversion. Right? So
Yes,
it's like
you can also see it here.
Oh.
Maybe I'll come back to it if I have time. Sure. Yeah, it would take a while to explain, but we'll see if we get there. Okay, but in particular, one sort of incarnation of this relationship between these things, JA and JB, which I forgot to say are called generalized complex structures.
is the holomorphic Poisson also visible?
Yes, I'll get to that soon as well.
Is it in one-to-one correspondence with?
Yes.
JA
Yeah, yeah. Given a pair,
With I plus minus and G. So on the left hand side we have JA and JB, on the right hand side
I plus minus.
and G.
That's right one?
Yes, exactly.
Because of the positivity of trouble.
Positive definiteness tells you something, tells you that G is positive definite. Yeah. This was a theorem in what theories? Yeah, so one sort of incarnation of this relationship appears by looking at the Dirac structures for L, for JA and JB, looking at their plus I eigenbundles. I have LA and I have LB, LA bar, and together this should give you the complexification of this bundle. See? But I also have LB bar, and I have LB, and because, I'm sorry, got one more thing, weaving pair. That's important. Okay, right. Because they commute, these decompose. Here, we'll call this L plus. And what you can, what these things L plus, L minus are really is they can be identified via projecting onto T with T01 of the complex, the complex manifold plus or minus. The notation x plus minus is n. So let me just give a name to this map and project some onto T onto the tangent bundle called rho. Inside here is T star.
So there was the notation T01 is anti-holomorphic holomorphic of the complexification, or
So
T01.
I mean, I'm just using X to denote the complex manifold M I plus minus. So here I'm taking T01 is the it's the minus I.
Well, this respect I plus and I minus the, which doesn't depend on it. Okay.
Yes, okay. Any other questions? So, okay, so we're going to use this later. So keep that in the back of your mind. But now let me say how we get to holomorphic Poisson structures. And there's,
In what sense is generalized Kähler? Oh, Kähler is inside.
a good question. Yeah, I didn't give any examples. So there's actually two ways in which Kähler embeds in generalized Kähler. One of them is by taking I plus equal to I minus. Then where does it go? I erased it already. Let's do that. You can take I plus equals to plus or minus I minus. Both of those will give you Kähler geometry.
All the way minimum plus minus.
Is consequence of the
Okay.
everybody speaks about Poisson structure. It's from the Poisson structure. It's not. Right. Okay. So everybody speaks about Poisson structure. In this case, I must ask, I don't understand it. Poisson structure on the product, on the direct sum. The classical Poisson structure, which
This is these are
non-deformed, induced, or
pi A and pi B are Poisson bivectors. They're bivectors on M,
okay.
which
Induced by GHB.
yeah,
Also, not H3s.
Yeah,
really, yeah, usual Poisson.
canonically inherited.
Yeah.
Okay.
Yeah, that's a funny thing. But that's important actually, that they're untwisted Poisson. And as is the holomorphic Poisson structure. And any holomorphic Poisson structure can be written by decomposing it into its real and imaginary parts, and that's what I'm going to do. And in general, the real part is related to the imaginary part in this way, just because it's a 2-0 tensor. General form you can give for a holomorphic Poisson structure, and then Q. Q is in this case, it's the imaginary part of the Poisson structure.
Yes, and that's to be
But
question.
I'm going to give you
Like holomorphic means it's holomorphic with respect to one of those two.
Yes, that's right. So
So sigma plus is holomorphic with respect to I plus.
and sigma minus is holomorphic with respect to I minus. And in this case, we want to take, in order to produce the holomorphic Poisson structure, we take this formula. So I'm just telling you that this, if you do this, you get a holomorphic Poisson structure. But this was also elegantly reformulated by Gualtieri. And he said that, well, first of all, holomorphic Poisson structures can be seen as generalized complex structures as well. So if I take, any tensor of this form, this will be generalized complex precisely when sigma, when I take the, when sigma is holomorphic.
Okay. And it's holomorphic because it squares to -1.
No, it's holomorphic because this thing is integrable. Integrability of this thing tells you precisely that this thing is holomorphic and it satisfies the, the integrability relation.
So how is J sigma related to the JAJB?
Yeah, that's good. That's next. Okay.
So sorry, one last question. So this J sigma is a generalized complex structure if and only if Q is holomorphic with respect to I. I is complex structure. Right?
Q is not holomorphic. Q is not even a 2-0 tensor. But sigma is a 2-0 tensor, and sigma is.
Sigma. But sigma is holomorphic with respect to I if and only this J sigma is generalized complex.
Yes.
That's
right.
Thank you.
Yeah, and then again here I want to put one plus minus back. I'm telling you, in particular, to produce the holomorphic Poisson structures coming from a generalized Kähler manifold, you take Q to be this. You take 5 plus minus here. And the way that Gualtieri produced these holomorphic Poisson structures is actually by looking at their plus or minus eigenbundles, L sigma plus minus. And these can be defined as the pullback of the diagram involving LA and LB. This is a diagram in Lie algebroids. There's a direct calculus which allows you to produce these pullbacks. Really taken, that's the definition. Okay. So I've gotten as far as oh, well, let me just observe why we can recover a generalized Kähler structure from sigma plus IA and IB. It's really sort of a stupid observation, but let me show you. If I take phi A plus IB, here, you're going to get I plus minus G inverse. If I take it the difference, then you minus IB, you're going to get I minus G inverse. And because the holomorphic Poisson structure should really be, in order to talk about a holomorphic Poisson structure, you have to first have complex structure. So in particular, when I say the data of sigma plus, I mean really the data of I sigma. So if I have one of these complex structures, then I'll immediately recover G, and from that I can also recover the other one.
Can I have the ordinary Kähler case, these three Poisson structures, like one of them is zero,
They're all zero.
they're all zero.
Is that right? Yeah, I think.
But then how can it be a from description?
Sorry, no, yeah, you're right. That's not right. Yeah, okay. In the ordinary Kähler case, what are they? If I plus is equal to I minus, this one is zero, but the other one is omega inverse, basically. So you can recover, you have the complex structure coming from one of the holomorphic Poisson structure that you have, and you combine it with omega to get recover G. Okay. That's the ordinary.
So in the ordinary case, one of the generalized complex structures is just like the complex structure as a generalized complex structure. And
That's right. Yeah. Yeah, that's right. Let me write that down because that's good. Guess I should have given all the examples. Generalized complex structures first. So let's do that. So you have a complex structure, you can always produce a generalized complex structure in this way. And similarly, if you have a symplectic structure, you can always produce a generalized complex structure like this. And this is how you recover generalized Kähler from here, in particular by combining these two.
JA, JB then defines a generalized metric, right?
Sorry.
JA, JB then defines a generalized metric, right?
That's right. Yeah. Yeah. The composition of JA, JB is what's called a generalized metric. Use that. Maybe I'll keep this up for a minute. So now I need to tell you what a Courant derivation is. I've gotten as far as h plus minus. So for this, I'm going to talk about what it really is. It's a symmetry of the Courant of full TM. It's an example of algebra, right? That wasn't clear. So the Atiyah, so this thing has natural pairing, first of all, and that gives you an Atiyah algebroid. Fits into an Atiyah into a sequence. So sections of this Atiyah algebroid are vector fields on the total space of this bundle, which preserve the pairing, the metric, pseudometric. And so here we have SO. And as we know, the special orthogonal of the algebra is just skew symmetric matrices. Now, so this sequence doesn't have a natural splitting. There's no way to naturally identify what. Yeah, there's no connection on this bundle, natural connection, and yet there is a way to identify sections of this bundle with pairs of vector fields and elements in here. The way that you do it is with the leader. So sections of the TF look like vector fields and elements in here. And the way that these act on sections of TM, let's call them section C. Is you take the Lie derivative of everything with respect to Z. And we take 5. And then you can ask, under what conditions do these things preserve the Lie brackets on TM? For derivation, D reserves. We got it. Courant brackets. Precisely. Well, first of all, we can decompose this into 3 parts. So, and the first thing that we need is that we need 5 to actually live in here. So it's going to be a 2 form. For some reason, I'll call it B. 2 form. And furthermore, we need that elements at H, bracket is H twisted, is equal to D. These are vertical solutions.
Would it simplify the picture if you use the Q manifold or the Q manifold description?
Yeah, okay, good. So the question assumes a familiarity with an important theorem, which is that Courant algebroids are related to symplectic supermanifolds of type 2. In fact, they're the same. Shift 2. And for that, this Atiyah algebroid is precisely
degree.
It's the functions of degree 2 on supermanifold.
Generate zero degree.
And the bracket gives you a differential on these functions. So you have some differential graded algebra. And D being in here preserves the bracket precisely when it's closed with respect to that differential. So this is a closed element of degree, a closed function of degree 2 of the supermanifold, if you go this way.
My opinion sounds a bit easier.
Sorry?
It sounds a bit easier.
Yeah, but that's a lot of background. I think Friedrich took a full semester to teach about that. Roughly.
So just omega 2, I don't really ask question. Omega 2 is just sections of page power of T star, the notation about.
Yeah, that's right.
Here,
Yeah.
the very last term. Okay. The sections are okay.
Sections of that, yes.
So the fact that there is a natural splitting is kind of comes from the fact that you are identifying.
Well, it's not a natural splitting, right? Because L isn't, it's not a vector bundle. Anyway. It's not a splitting of the sequence. But it's still, you can identify. Yeah,
And does it use the fact that we are identifying the exact algebra with double TM?
yes,
So if you do that,
yes.
you
For this talk, all Courant algebroids are TMs. I haven't told you about any other ones. So now I'd like to tell you about some ways you can produce these symmetries. And the main way we're going to produce them is using generalized connections. There is something. So what is a generalized connection? So roughly speaking, we defined generalized complex structures by imagining that this old TM was really the tangent bundle and defining complex structures of that thing. So we're going to do the same thing with generalized connections. So these are going to be maps on some vector bundle. Actually, for us, it will just be a line bundle. We're going to go to sections of T. And you can dualize it if you want, but it doesn't matter. It's the same. Such that it's Leibniz rule where I differentiate, let's say it's plus C. If I differentiate some F B, this is going to be F plus F. So that only the vector component this element maps on functions. And so these have curvatures that are given by. Let me just call this element or an element here U. I'm going to change my notation. This is going to be a section S. So R B is going to be an element here. A section of T. And we take the usual formula curvatures, but now we're going to use the Courant. And what we find is that this thing is, it's not tensorial in this argument, which some people might say is an issue. I disagree. I think it's fine. That's really a differential operator. And in particular, this differential operator, if I write this way, oh, sorry, it's not tensorial, this argument. It's, sorry.
So the correction is not a connection if x is 0. If I make plug in x 0, I get the number side.
That's right.
As it's just
Okay, you made an important observation. Meaning,
so okay, but I can accept the name.
sorry,
I can accept the name that it is called connection and
you can't accept it. Let me maybe expand on your observation, which is that, okay, I can decompose into T plus T star. Really, this generalized connection has two components, one coming from plugging in vectors into it and one from plugging in covectors. And the one from plugging in vectors is going to actually be a real connection. On the other hand, if I plug in a covector, yeah, you're right, it's linear because this term vanishes. And it really is going to be just a vector field. Section of T, that's and B. For us, N to B is line bundle, so this is just going to be a vector field. So that's all these things are pairing connection with a vector field. And yeah, because they're tensorial in this argument, you can write it as by pairing with the metric. You write it as a differential operator. And that differential operator actually preserves that differential operator preserves the pairing on Tm, on both Tm. So T is a section of the operator. And moreover, there's a Bianchi identity, which tells you that D preserves bracket. So it's a symmetry of the whole Courant algebra. It's a Courant derivation. So this is going to be the main way that we produce these things. And let me give a subclass relating to generalized complex structures. So if V is now a holomorphic vector bundle, and H is a Hermitian metric, then as you know, or as you may know, there's a unique connection whose 0,1 component gives you the Dolbeault operator on this vector bundle, which preserves the Hermitian metric. That's well known. If instead it's not holomorphic, but it has a Delbar operator, which is now a flat L connection for some generalized complex. That was my generalized. Then there's also a unique generalized connection which preserves H and has its L component being del bar. It's called generalized churn.
When by L connection you mean that L is Lie algebraic or
L. So whenever I have a generalized complex structure, it has plus an
yes.
eigenfunction.
You have the-
Both of which are
yeah.
the algebraics.
So it's a connection of this on this Lie algebraic corresponding this plus I.
It's a the algebraic connection.
Yeah.
So this gives me a way to produce these connections, and in particular, their curvatures not only preserve the bracket and the metric, but they also preserve the generalized complex structure that you started with. The curvatures are very nice objects. So, and the main example comes from spinners.
Chain connection in complex geometry, not in quaternion complex geometry. Chain connection in complex, on complex manifolds.
Yeah, in this case, I was talking about the churn connection on complex manifolds.
Yeah.
Here now I've moved to generalized complex manifolds, which have a generalized churn connection. As you say, it's not a connection, but it's actually a connection plus a vector field. And so one nice thing about this old TM is that it acts on the differential forms. Let's see. By we contract the vector field part and wedge the one form part. And this extends to an action of the Clifford algebra. Just have to check the Clifford relation. And so the differential forms are really spinners for this TM. And in particular, you can look at the line, the spinner line, annihilated by L. And this is called the canonical line bundle of the generalized complex structure, and it has a generalized holomorphic structure on it. I don't have time to explain, but well, and in the case you have a Hermitian metric, well, in fact, any Hermitian metric can be written here, written as alpha wedge beta transpose take the top component. This gives you something valued in determinant of T star with volume form, but if you divide by some volume form, what's conjugate, you get a Hermitian metric on this canonical bundle. And then what we know is that this is a proposition that pi is minus I over 2 x pi, where x pi is the modular vector field for pi, and pi is the Platonov structure determined by J. So the same way that we got pi A and pi B, any generalized complex structure gives you a Poisson structure. And if you compute its modular vector field with respect to mu, you produce that vector field. The general term. So I want to be able to actually, I want to be able to actually write down what is the derivation, with the Courant derivation that you need to use to produce generalized Kähler Ricci flows. So let me do that in the last 3 minutes. So generalized Kähler geometry, you have these two generalized complex structures. So you have a pair of canonical bundles in the spinors. And they fit into this broader decomposition of the differential forms. So what it looks like here, Ka, Kb, I have their complex conjugates. And in between them, I have lots of other differential forms. But in particular, because inside Tm, I have these 4 subspaces, which I just erased, like L plus, L plus smaller, L minus, L minus smaller. These all act in a different direction. Their Clifford action brings you in a different direction in this space. L minus in this direction. And to get from Ka to Kb, you have to need determinant L minus, which was the same thing as the canonical bundle of I minus by this identification. I think I want the arrow the other way around. Okay, so we have this relationship between Ka and Kb, which is given by the canonical bundle of the usual complex structure. Ka plus K here Kb. And so now, because we have here, I have an LA module structure. Here I have an LB module structure. It seems that there's no way to combine them to get any structure here, except that we have these diagrams relating LA and LB module structures to L sigma plus and L sigma minus. Anytime I have an LA module, I can produce an L sigma plus module. Similarly for AB. So in fact, K minus, it has a whole bunch of connections on it. And one of them is an L sigma plus module structure. And so from that, you can produce a generalized term. Now, it's on the bundle minus the K minus bundle, and it's a generalized term with respect to sigma plus. So we'll denote it like this. We're going to have curvature plus, which in particular preserves L sigma plus. So, in fact, even more is true that when I act on this triple by R minus plus, it preserves sigma plus, but it deforms pi A and pi B. So I'll stop there, but that is the content of the theorem is that this is the derivation which drags around these 3 Poisson structures to produce this generalized Kähler Ricci. Good. Questions?
Regarding the spin-offs, yes, because the dimensional computation, preferred algebra of the tangent, bounded tangent bundle of n of the
Yeah.
bounded Tn is 2 to the power 4n dimensional in the sense of complex. Yeah.
Yeah.
And so it must have, and it is associative, simple algebra. So it has one element, which is 2 to the power 2n dimensional complex. And these are the spin-offs.
Yes.
And there are sums of spin-offs. For example, in dimension 4, there are sums of this S plus file and S minus file. So,
Yeah, because even in odd differential forms, those two decomposition into S plus and S minus.
but that's not the issue. The L lives on the bounded Tm or on the
Complexification.
on the complexification of the bounded Tm. Yeah. So the spin-offs are the complex ones. Yeah. Are the
Yes, yeah. I should say, yes, here I'm complexifying everything.
So, part of what you're saying was that for any generalized complex structure, you can get a determination bundle. So there is that mu thing entering there, right? So,
Yes.
So is it true that the connection, the generalized term connection, like the vector part of it will depend on mu?
Yes,
Okay.
yeah, exactly. Precisely because the modular vector field, the way you define a modular vector field,
Oh, is it there?
okay,
Okay.
I would have done. Where's the so phi thing. It's a vector field, so it acts on functions, and the way you define it is that you take the Hamiltonian vector field of F, and you act on mu, differentiate mu, and then you divide by mu, and that gives you. This is what the modular vector field is.
And can you also say what the ordinary connection part of this term connection is? Did you say?
It's easy to say you have to have more information about what
Okay.
case you're in, but
Does it depend on mu anyway?
it will depend on mu, yeah.
Okay.
So in the case, for example, in the holomorphic Poisson case, if your generalized complex structure is holomorphic Poisson, then in particular, an L connection, flat L connection, or a generalized holomorphic structure, gives you a holomorphic structure on the bundle. So your bundle is ultimately holomorphic, and therefore it has a Chern connection, and it's that.
Okay.
That's it.
So if I ask you for the terminology spin-off line, yeah, so it is a really rank 1 complex line bundle, which is a top form bundle of Tn non-complexified Tn plus. But normal spin-offs are maybe annihilated by some distributions, but they are almost never sort of dimension 1 bundles of rank 1. So spin-off line is a terminology. Just
It's possible I'm using the wrong terminology. I just mean that if you look in the differential forms, for those differential forms which are annihilated by L, you get a line bundle,
yeah,
which completely determines the generalized.
let's go spin-off. Also, it cannot generate any spin-off.
Well,
Because it is one dimension.
it's one dimensional, yeah. It's
So
sub-space. It's sub-bundles of spinors. Yeah, I don't know, call it what you like. I didn't make up the terminology. So.
So instead of for Kähler modules, you have the Kähler identities, which imply the equality of the two Laplacians, but up to a scalar.
Yes.
Some sort of generalization of that.
Yeah, there are Kähler identities in here. I didn't get to say. I didn't get to say why these canonical bundles have this generalized holomorphic structure. And the reason they do is that it doesn't come from the Durand differential on here, but instead from the twisted Durand differential. So what you do is you take d h, equals d plus h wedge. This is an operator on the differential forms, which doesn't preserve the Z grading anymore. That's broken, but it's still Z2 graded at least. And with respect to this decomposition of the differential forms, this decomposes into 4 pieces going in different directions. So you have like a del r minus so you have all these operators, and using a Hermitian metric, this one, you could produce a whole Hodge theory for these operators, and there's Kähler identities there.
And then like are they associated with Laplacians? Then
Yes.
the D they coincide with the scalar again.
Yeah, that's right.
And when you question, you have Kähler geometry, but then you have the analogous quaternionic version, the quaternionic Kähler geometry. If there's a generalized version of this.
There, I don't know about quaternionic Kähler. There is something. There's such a thing as generalized hyperkähler.
Okay.
But I don't think anyone's really spent much time studying it.
So that's
Maybe some physicists, but not really.
Say a bit about why split this Kähler which is not tensorial and like a tensorial correction.
Yeah, so there is one way of handling this non-tensorialness that people have done is by adding terms to make it tensorial. I mean, that maybe is useful for some things, but I think it, from my perspective, it kind of obscures what the actual operator is. The fact that it's not tensorial shouldn't worry you because it's a section of some vector bundle. So, and that vector bundle is well understood. It's not anything.
So does it break down if you add the new terms, or is it just?
Yeah, it won't be a symmetry of the Courant algebra in any full way. So, yeah, I think something is lost by adding those terms.
Any other questions? Also from the online audience? Well, then let's thanks.